Hello friends, I am Dr. Sudhansh Sharma from School of Computer and Information Sciences, Indira Gandhi National Open University, and this session is about solution of system of linear equations. In the last sessions, we had learned about the concepts of determinants and matrices. Now, herein we are going to apply those concepts to solve the system of linear equations. Now, the objectives of this sessions are about to determine the inverse of a matrix, and by using this concept of the calculation of the inverse of a matrix, we are going to solve the system of linear equations. Wherein we will learn about what is system of linear equations. We had already discussed about this in our earlier sessions, wherein we discussed about the homogeneous system of equation, inhomogeneous system of equations, and all that. Now we will be using the concept of matrices, inverse of matrices, to solve the system of linear equations. Now, what are invertible matrices? Now, actually, invertible matrices are also known as non-singular matrix, and these are the matrices of order say n cross n, and say A is a matrix of order n cross n. Then there exists a matrix B of order n cross n such that A into B is equal to B into A is equal to an identity matrix. So that means B is inverse of A. So A inverse B, A inverse into A will be by applying the rule of the exponent. We will say that you can say that the powers will be added, and this will be a to the power 0, and a to the power 0 is nothing but an identity matrix. So we are applying the rules of exponents, and we will find that a to the power 0 is an identity matrix. Therefore, a B is equal to A inverse is the inverse of matrix A. Now, there might be a situation when there are non-invertible matrix, and non-invertible matrix are also called singular matrix. Now we apply the understanding to solve some numericals. Likewise, over here one numerical is given that find whether A is invertible or not, where A is given. In case A, it is 1101. So in order to find that whether it is invertible or not, so we because we use the understanding that B in A into B is equal to an identity matrix. So B is, say, any hypothetical matrix whose values are A, B, C, and D, as given over here, such that A into B is equal to an identity matrix. So that means identity matrix is a matrix whose diagonal elements are 0, 1. So if we solve this expression, that is A into B into identity matrix, you can say that you will get this is an identity matrix, and we are having expression A into B, where A is 1 1 1 1 0 1, and B is A B C D. Performing the multiplication operation, that means we learned about the multiplication operation in our earlier session also. We perform this into this plus this into this. That means 1 into A plus 1 into C. So you will get A plus C. Similarly, 0 into A plus 1 into C. So 0 plus C, that is equal to value C. Similarly, 1 into B plus 1 into D, that is B plus D. 0 into B plus 1 into D, 0 into B plus 1 into D. So that means you will get the value D. So overall, we get the result AB as a new matrix whose values are A plus C, B plus D, and C and D. Now we equate the values one by one, and we will find that equating the values, we will get A plus C is equal to 1, 0 will be equal to B plus D, 0 will be equal to C, and 1 will be equal to D. So that means we get C is equal to 0 and D is equal to 1. Now using these two expressions in the equations, A plus C equal to 1 and B plus D equal to 0, we can get the values which are like this. So that means by solving these two equations, we can get the values D equal to 1, C equal to 0, A equal to 1, and B is equal to minus 1. So our matrix B was A, B, C, D. So that means B is equal to 1, minus 1, 0, and 1. and this is nothing but A inverse. So B is equal to 1 minus 1, 0, 1, and this satisfies the identity B in A into B is equal to an identity matrix In. So that's why B is inverse of A, because we are getting B into A. Now we can verify that B into A, whether we are getting the result as an identity matrix. So substituting A and B over here, this is matrix B, this is matrix A, then performing the multiplication, we are getting an identity matrix. This means that B is inverse of A. So we had verified also that the B is inverse of matrix A. Now let's extend our discussion to solve another problem which is given over here as section B, and in part B the value of A, which is to be checked that whether it is invertible or not, is this, that is 1 0 and 0 0. So let's assume that B is A B C D, which is again inverse of the matrix, given matrix A. So we again apply the same thing, that this is an identity matrix and A into B should be equal to identity matrix. Given value of A is this, and we assumed value of inverse of matrix A is B. Now after performing the matrix multiplication, 1 into A plus 0 into C will be A. Similarly, 1 into A plus 0 into C is 0, is A. So that means after performing the matrix multiplication, you will get the result as A, B, 0, 0. Now the observation is, after comparing the values with the identity matrix, which is 1, 1, 0, 0, you will see that the value of A turns out to be 1. A is equal to 1. And B turns out to be 0. But if we go for other combinations, likewise, over here the observation is, over here the value of D is 0 and value of D over here is in diagonal element is 1, and 0 can never be equal to 1. So that means there is no such B exist in particular, hence A is non-invertible. So this matrix is non-invertible and this one is invertible. I hope you got it. Now we apply, we'll try to understand one more thing. There is a theorem that if a matrix has an inverse, then that inverse is unique. This is an important theorem, and let's understand it, what this theorem wants to say with the help of a proof. Say we assume that in order to prove that the inverse is unique, we assume that there are, say, two inverse, say B and C be the inverse of matrix A. So if there is an inverse, B is also inverse of A and C is also inverse of A, then AB should be equal to BA should be equal to an identity matrix. Similarly, AC should be equal to CA should be equal to an identity matrix. Now the property of the identity matrix is, say, B is equal to B into In. If we multiply by any matrix with an identity matrix, the matrix will remain same, as if in the case if we multiply any number by 1, the number will remain same. So that means if we say that B is equal to In, and by using the equation number 2, what equation number 2 says that In is equal to AC is equal to CA. So if we replace In, that is identity matrix, by A into C, we can say that B into In is equal to B into AC. And by using the associative law, we can write BAC as BA into C. Now referring to equation number 1, now BA is equal to identity matrix, so BA is nothing but an identity matrix. Now identity matrix into C will be equal to C itself. So that means B, what was carried forward over here, that B is equal to this, B is equal to this, so B is equal to C. So that means by using this, we can say that both B or C are same. That means the inverse is unique. So that's why A into A inverse is equal to A inverse into A is equal to an identity matrix. Now we use this expression to find the inverse again, and we will extend our discussion. But before that, we need to understand what do we mean by the cofactor matrix, because the understanding of the cofactor matrix will be applied to find the adjoint of a matrix. What is adjoint of a matrix, how adjoint of a matrix is used to calculate the inverse of a matrix will be discussed shortly. So we learned in our earlier sessions that cofactor of a matrix Cij will be equal to minus 1 to the power I plus j into Aij. Yes, I think you are able to recall this expression. So let's calculate the cofactors first. Now, what is to begin with? Let's formally discuss what the definition of cofactor matrix is. A matrix A is equal to Aij n cross n be a square matrix of dimension n cross n. The cofactor matrix of A is defined to be a matrix C is equal to Aij n cross n, where Aij denotes the cofactors of the elements of Aij in the matrix. So nothing is to be worried about. You simply need to calculate the cofactors and put the values over there into the matrix itself, and you will get the cofactor matrix. So if A, let's understand with the help of an example. In this example, the matrix A is given over here 1 minus 2 1 3 0 5 and 4 minus 1 2. So the cofactor 1 1. So 1 1, first row, first column. So that means minus 1 to the power 1 plus 1, that is I plus j, and remaining determinant is this 0 5 minus 1 2. Now if we calculate this into this minus this into this, that is 0 minus 5 into minus 1, that is equal to 5. So cofactor 1 1 cofactor is 5, and this is the 1 1 C11, or you can say A11. Similarly, you can say that this is C11. Similarly, you can say C12 or C13, whatever cofactors, so as to have the better readability. So C12 is again first row, second column. So you just recall what how we had calculated the cofactors in our earlier session, that this is first row and second column. The remaining values are these. So minus 1 to the power I plus j, that is first row, second column, and remaining values are 3 4 5 2. Calculating these two, 3 into 6, 5 into 4, that means minus this turns out to be 6 minus 20. So then minus 1 to the power 3 is again minus. So this turns out to be 14. So the 14 is the value. So I hope you are able to understand how to generate the cofactor matrix. Now you might be thinking that when we had already discussed about that what cofactors are, why we are discussing about the cofactor matrix again. The understanding is that in order to calculate the adjoint, we need to have the calculation for the cofactor matrix. So what is an adjoint of a matrix? The adjoint of a matrix of any matrix A is defined as the transpose of the cofactor matrix. I hope you understand that why we had calculated the cofactor matrix. Firstly, calculate the cofactor matrix, take the transpose of that cofactor matrix, and what you will get? You will get the adjoint of the matrix A. So you, just see it over here, A11, A11, this is a cofactor matrix. This is a transpose of the cofactor matrix. So we learned about what cofactor matrices are, and now we extend our discussion to understand what do we understand by adjoint of a square matrix. Now actually adjoint of a square matrix is actually defined as the transpose of a cofactor matrix. That's why we learned to calculate the cofactor matrix. So if any matrix A is given and say A11, A12, A13 are the cofactors, A11, A12, A13, A21, A22, A23 and A31, A32, A33 are the components of the cofactor matrix. Then transpose of the cofactor matrix is adjoint, wherein you will see that these rows are transformed into the columns. So transformation of rows into columns leads to the of a cofactor matrix leads to the adjoint of a matrix. Now there is a theorem that A into adjoint of A into adjoint of A, or adjoint of A into A, it will be equal to determinant of A into identity matrix. So we had already learned that we use the expression B into A is equal to identity matrix, then B is equal to A inverse. Or we are also learned that A inverse into A or A into A inverse is equal to an identity matrix IN. So that means we can write the expression adjoint of A into A is equal to determinant of A into identity matrix as adjoint of A upon determinant of A into A is equal to identity matrix. This implies this value is nothing but A inverse. So A inverse is adjoint of A upon determinant of A. And what is adjoint of A? Adjoint of A is the transpose of the cofactor matrix of A. So, and one more important thing is that determinant of A should not be equal to 0. We also learned in our earlier sessions that how we use the cofactors to calculate the value of the determinant. In the past sessions, we had discussed that if there is a matrix whose cofactors, say if there is a matrix A, then you can multiply A11 into A11 plus A12 into A12, where A11 and A12 are the cofactors, will give you the determinant of A. We will re-explore this expression when we are going to solve the numericals in the upcoming slides. Let's apply the understanding to solve one of the numerical over here. Find the inverse of matrix which is given to us is 3, 2, 10, 7. Now, firstly, we try to calculate the determinant. Now, because the foremost requirement is determinant should not be equal to 0. Why should it not be equal to 0? Because A inverse should be equal to adjoint of A upon determinant of A. So that's why, because determinant is occurring into the denominator, so it should not be equal to 0. If it is equal to 0, then infinite result will be there. So determinant of A will be equal to this into this minus this into this. So 7 into 3 minus 2 into 10. So that means 7 3 are 21 and minus 2 into 10 is 20, 21 minus 10 is 1, which is not equal to 0. So one condition is satisfied. Now second condition is we need to calculate the adjoint. For adjoint, we need to firstly calculate the value of the cofactors. So let's calculate the value of the cofactors. So first and the foremost is A11. Say A11, that is equal to 1 1 minus 1 to the power I plus j, that is equal to minus 1 to the power 1 plus 1 1 plus 1, and the remaining element is 7. A12 minus 1 to the power 1 plus 2, first row, second column, first row, second column. So remaining element is 2. A21, second row, first column. So minus 1 to the power 2 plus 1 and 10. A22 minus 1 to the power 2 plus 2. So 2, 2, and the remaining element is 3. 2, 2, so remaining element is 3. So first value will be 7, second value will be minus 2, third value will be minus 10, fourth value will be 3. So cofactor matrix will be A11, A12, A21, A22. That is equal to 7 and 1 2 minus 2 and 2 1 minus 10 and 2 2, that is 3. Now adjoint of A, this is a cofactor matrix, this is cofactor matrix. Now adjoint of A will be transpose of this. So transpose will be 7 minus 2 minus 10 and 3. So this is adjoint of A. So adjoint of A is calculated over here. Now A inverse will be equal to adjoint of A upon determinant of A. So adjoint of A is, the determinant of A is 1 and adjoint of A is this 7 minus 10 minus 2 3 and this is 1 divided by 1. So A inverse will be equal to 7 minus 2 minus 10 and 3. You can verify it by performing the matrix multiplication and you can check that A inverse into A is equal to identity matrix or not. You can check it yourself by multiplying A inverse with A. Okay. So now let's solve one more example wherein we are supposed to find the inverse of another matrix. Or again on the same line of action, we are calculating. Now we are over here, we are going to recall that formula. In earlier side, we calculated the determinant of A. We calculate the determinant of A by multiplying 3 into 7, this into this minus this into this, and we got the value this. Now over here we are using the cofactors A11 into cofactor A11 plus A12 into cofactor A12. We discussed that why we calculated the cofactors, because when we are calculating the determinants in a normal way, the change in polarity of the sign plus minus plus goes on. In order to remove this change in polarity of sign so that total result remains in the additive format, we calculated the cofactor. So determinant can also be calculated by A11, where A11 is this and A12, A first row second column, that is A12 will be this, and A capital A11 capital A12 are the cofactors. So what will be A11? A11 will be equal to minus 1 to the power 1 plus 1, 1, 1. So remaining element is 4, and A12 will be 1, 2 will be minus 1 to the power 1 plus 2 into 2. So that means equal to A11 will be equal to 4 and A12 will be equal to minus 2. So this is minus 2 and this is 4, and determinant value will be equal to A11 into cofactor A11 plus A12 into cofactor A12. So what is A11? A11 is minus 3. A11 is minus 3. And this is capital A11 4 and A12 is 5, A12 is 5 and capital A12, that is cofactor, is minus 2. So performing the calculation, you will get the answer minus 22, which is not equal to 0. So that means determinant A is not equal to 0, which is satisfied condition. Now we need to find the other cofactors so as to determine the adjoint of A. So determining the adjoint of A, we got, that means the transpose of the cofactor matrix, we get adjoint of A as 4 minus 5 minus 2 minus 3, and again A inverse is equal to adjoint of A upon determinant of A, adjoint of A upon determinant of A, and this leads to the result minus 2 by 11, 5 by 22, 1 by 11, 3 by 22. I hope you got an idea how to calculate the inverse of matrix. Now we extend our discussion for the calculation of the inverse of matrix to and apply it to solve the system of linear equations. We on our earlier sessions we also learned that what are linear equations. Linear equations are the equations wherein the exponent value of the variable is 1. Over here x1 is having power 1, x2 is having power 1, x3 up to xn all are having power 1. So this is a linear equation. Ax plus b is equal to 0 is a linear equation. So x is equal to minus b by a. So this is a linear equation. But in case we are having the exponent value, say x square, ax square plus bx plus c. Now over here the exponent value is 2. So that's why the equation is quadratic. So we will not be discussing quadratic equation at this moment. We will be discussing about the quadratic equation in the later sections. So if these are the systems of equation, and we had also discussed in our earlier sessions that if b1, b2, b3, bn are not 0, then the system is inhomogeneous, and if b1, b2, b3 to bn are 0, then the system is homogeneous. We can express this system of equation in the matrix form over here like this. So a11 A12 up to A1n, A21, A22 up to A2n. Similarly, AN1, AN2 up to ANN into X1, X2 up to Xn. We will get it equal to B1, B2 up to Bn. So this is the system of equation. This is the matrix representation of the system of equation. Now, because we got the system of equation as Ax is equal to B, Ax is equal to B. So what could be the possible solution? X is equal to A inverse B. In order to solve the system of a linear equation when A is non-singular, that is invertible, then what we are showing, we are using this expression Ax is equal to B, then X will be equal to A inverse B. So that means this is the solution of the system of linear equations. Solution. So Ax is equal to A inverse B is the solution of system of linear equation. So this is what is expressed over here, that we can transform the system of linear equation Ax is equal to B into a manner where X is equal to A inverse B, which is the solution. So let's apply concept of A inverse B to solve a system of linear equation. Given system of equation, we are having two equations, x plus 2y is equal to 4 and 2x plus 5y is equal to 9. Now transforming it into the matrix representation, we can say 1, which is the coefficient of x, 2, 2, 5, x, y is equal to 4, 9. So this is A, this is x, this is B. So we need to calculate x because x is a solution, where it will be equal to A inverse of B. So that means we need to calculate A inverse, and in order to calculate A inverse, we need to calculate adjoint of A, and it is to be divided by the determinant of A. So applying all these concepts, that what is cofactor matrix, what is adjoint of A, which is the transpose of the cofactor matrix, and how to calculate the determinant, then we will come up to a solution wherein this system Ax is equal to B is to be solved, where A is equal to 1, 2, 2, 5, and the cofactors of the matrix A are A11, which is 5, A12, which is -2. So using the expression which we had discussed, that determinant A is equal to A11, that is this value, into cofactor A11, that is this value, A12, that is this value, that is 2, into cofactor value A12, we will get the determinant 1 into 5, 1 into 5 plus 2 into -2, which is equal to 1, which is not equal to 0, and the requirement to calculate the inverse is determinant of A should not be equal to 0. Now we calculate the other values of the cofactors also, A21, which turns out to be -2, and A22, which turns out to be 1. Taking the transpose of the cofactor matrix, we got the determinant, we got the adjoint of A, which is 5, -2, -2, 1. And we know that A inverse is equal to adjoint of A upon determinant of A. So applying the solution, we got A inverse as this is the value of A inverse. Now we need to find the solution. So that means we need to get the value of x. What is x? X is equal to A inverse B. And what is A inverse? This is our A inverse. So that means x is equal to 5 into -2 into 1, and what is B? That is 4 into 9. So again matrix multiplication is performed. This is 2 cross 2 order, this is of order 2 cross 1. Number of columns of first is equal to number of rows of second, so matrix multiplication is possible. Apart from this, the order of the resulting matrix will be 2 cross 1. That means we'll be having 2 rows and 1 column. Yes, this is having 2 rows and 1 column. So by having matrix multiplication, we got the result. By multiplying these two, we got the result 2, 1, and our matrix X is equal to XY, and which turns out to be 2, 1. So that's why value of X is equal to 2 and value of y turns out to be 1. So x is equal to 2 and y is equal to be 1. I hope you understand this. Now, as we had already discussed that when the right hand side of the linear equation turns out to be 0, then the system of linear equation is homogeneous. So, that means the matrix B, Ax is equal to B, the matrix B is 0 in the homogeneous system of linear equations. And based on that, you will get that the values of x turns out to be 0, and which is nothing but a trivial solution. So, because A inverse into B will be equal to 0. So, this means that A inverse into Ax is equal to A inverse into 0, that is 0 matrix. So, that means A inverse A into x is equal to 0, and A inverse A is nothing but your identity matrix. So, that means x is nothing but 0. So, the trivial solution is x1, x2, x3 all are 0. I hope you understand this. Now, applying the understanding to solve this system of homogeneous equations, we are given three equations: 2x minus y plus z equal to 0, 3x plus 2y minus z equal to 0, and x plus 4y plus 3 equal to 0. So, writing the equations in the matrix format. So, writing the coefficients first: 2 minus 1, 1, 3, 2, minus 1, 1, 4, 3, and then x, y, z is equal to 0, 0, 0. So, this turns out to be Ax is equal to 0. So, again we need to solve it. So, that means again we are supposed to find the cofactors. So, we found A11, A12, A13. So, the determinant A will be equal to A11 into A11. So, A11 is, small a11 is 2 and capital A11 is 10, small a12 is minus 1 and capital A12, that is cofactor, is minus 10, and small a12, that is element value of A is A13 is 1 and the cofactor A13 is 10. So, that means 2 into 10 minus 1 into minus 10, 1 into 10 turns out to be 40. So, that means determinant A is not equal to 0 and it is A is, that means A is invertible, A is non-singular. So, because x turns out to be 0, by using this theorem, by using the understanding when we are having the trivial solutions, we will get that x is equal to 0, y is equal to 0 and z is also equal to 0. So, there are some of the important results which are concerned about the solution of system of homogeneous linear equations, where Ax is equal to b and b is equal to 0. They are given. Likewise, the first important observation is, if A is singular, singular means non-invertible, then Ax is equal to 0 has infinite number of solutions. Why infinite number of solutions? Because determinant of A is equal to 0 and A inverse is equal to determinant adjoint of A upon determinant of A. So, if determinant A is equal to 0, then there are infinite number of solutions. Conversely, if Ax is equal to 0 has infinite number of solutions, that means A is singular matrix, that means it is non-invertible. And if we are having adjoint of A into B equal to 0, then Ax is equal to B has infinite number of solutions, and that is consistent, that is self-explanatory. And if A adjoint of A into B is not equal to 0, again that means Ax is equal to B, the system of equation has no solution and it is inconsistent. In order to brief all the possibilities in the form of a graph, this picture summarizes all that we are having a system of equations, say Ax is equal to B and determinant of A is not equal to 0, then x is equal to A inverse B is a unique solution and it is consistent. But if determinant of A is equal to 0 and then adjoint of A into B is also equal to 0, then we are having infinite number of solutions. Apart from this, if adjoint of A into B is not equal to 0, then there is no solution. So, this is all about the concept of solution of system of linear equation, and in this session we learned about how to determine the inverse of a matrix. Apart from this, we also learned about how to solve a system of linear equations. We also revised about understanding of the cofactors, how to determine a cofactor matrix, and how to use the cofactor matrix to determine the adjoint of a matrix. Thank you very much.